Hello. This will be a demonstration of proposition 15 from book 9 of Euclid's Elements, which says that if three numbers be the least in a continued proportion, then the sum of any two of them is prime to the remaining number. We're going to have three numbers a, b, and c, which are the least in a continued proportion, such that a is to b just as b is to c. And what we want to prove from this is that the sum of any two of these numbers is prime to the third one, that a plus b is prime to c, that b plus c is prime to a, and a plus c is prime to b. We're going to begin by taking the two numbers de and ef, which are the least in the same ratio as a, b, and c. We can, of course, find de and ef by proposition 733. Now, because de and ef are the least numbers in the same ratio as a, b, and c, we can say by the porism of proposition 8.2 as well as some other work that a is equal to de squared, that b is equal to the product of de and ef, and finally that c is equal to the square of ef. How we would get that a is equal to de squared and c is equal to ef squared simply follows from the porism of proposition 8.2 on its own. It simply says that. And how we get that the middle term b is equal to the product of de and ef. You can see this play itself out in proposition 8.2, but you can also look to proposition 8.11, that between two square numbers, there's of course one mean proportional, and that one mean proportional is equal to the product of the sides of the two squares. So the sides of the squares being de and ef, the middle term b is going to be equal to the product of de and ef. Now with that out of the way, we're going to remark again that because de and ef are the least numbers in their ratio, we know that they are because of how we made them. We know by proposition 722 that they are prime to each other, because prime numbers are the least in a given ratio. Which then means by proposition 728 that their sum is prime to each of them. That's what proposition 728 tells us. So that because de and ef are prime to each other, their sum df is prime to each of them, de and ef. But what we have here are the two numbers df and de, which are both prime to ef. We can get that from our previous step. And we know by proposition 724 that if two numbers are prime to a third number, then the product of the first two numbers is also prime to that same third number. So that because df and de are both prime to ef, the product of df and de is also prime to the product of df and de is prime to ef. And we also know that if two numbers are prime to each other, the first is also prime to the square of the second. That's what proposition 725 tells us. So that because the product of df and de is prime to ef, the product of df and de is also prime to the square of ef. But we know that the product of df and de is equal to the square on de together with the product of de and ef. We get this actually from proposition 2.3. Now, you might be asking yourselves, why does that work? I mean, proposition 2.3 is about lines and squares and rectangles. So how can that possibly help us to make a statement about some numbers? We'll get to that at the end of the proposition once I've finished demonstrating this. But for now, we're just going to take it that the product of fd, or df, and def is equal to the square on de together with the product of de and ef. Because that's the case, we can substitute that in for our previous statement at the end of step 4 to say that the square on de together with the product of de and ef is also prime to the square on ef. But we know that de squared is equal to a, that df times ef is equal to b, and that ef squared is equal to c. We had established all of that in our second step. So we can simply plug those all in for our statement and say that a plus b is prime to c, which is the first statement we set out to prove. Now the second statement, that b plus c is prime to a, we would prove in a similar manner. We would just start by changing at step 4 that instead of saying that DF and DE are both prime to EF, we would have DF and EF both being prime to DE. We would take the products and the squares accordingly, and by the end of it, we would get that B plus C is prime to A. Now, because we proved that in the same way we proved the previous statement, we're not going to go through it again. But this final statement that we want to prove, that A plus C is prime to B, we're going to have to go about that in a different way. We begin by noting that the two numbers DE and EF are prime to DF. We had established that in our third step. And again, we know from proposition 724 that if two numbers are prime to a third number, the product of those two numbers is prime to the same third number, so that because both DE and EF are prime to DF, the product of DE and EF is prime to DF. But again, we know from proposition 725 that if two numbers are prime to each other, the first number is also prime to the square of the second, so that because the product of DE and EF is prime to DF, we can also say that the product of DE and EF is likewise prime to the square on DF. But we know that the square on DF is equal to the sum of the squares on DE and EF together with twice the product of DE and EF. We get this from another book 2 proposition, proposition 2.4, and how that helps us, a statement about lines and squares and rectangles, helps us to make a statement about numbers. We'll again get to that at the end of the demonstration. But the point is that the square on DF is equal to the square on DE plus the square on EF plus twice the product of DE and EF, which then means we can plug all of that in for the statement at the end of our 8th step and say that DE squared plus EF squared plus twice the product of DE and EF is prime to the product of DE and EF. We next want to prove that DE and EF, the squares on DE and EF are prime to the product of DE and EF. For if this is not the case, then there will be some number which measures the both of them. We'll call this the number G. G will measure both DE squared plus EF squared and the product of DE and EF. And because this is the case, that the number G measures DE squared plus EF squared, it measures that one number, and the product of DE and EF, it's also, by a property of numbers, going to measure DE squared plus EF squared plus twice the product of DE and EF. You can think of it like, how would this go? That 3 measures both 6 and 18, so it's going to measure 6 plus twice 18. That would be the sort of statement we're looking for. That would be that, let me go through that again. So 3 measures both 6 and 18. What this step here is equivalent to saying is that 3 measures 6 plus twice 18, which is the number 42. And 3 does measure 42, so we can verify that this step holds. That the number G measures DE squared plus EF squared plus twice the product of DE and EF. But we also know that the number G measures the product of DE and EF on its own, which means that the two numbers DE squared plus EF squared plus twice the product of DE and EF, that one number, and the product of DE and EF on its own have a common measure, which means that they are not prime to each other, which is contrary to what we established at the end of step 9. And so what ends up happening is that DE squared plus EF squared plus twice the product of DE and EF is both prime and not prime to the product of DE and EF, which is obviously an impossible state of affairs. And so we can conclude that DE squared plus EF squared are therefore, or that one number is prime to the product of DE and EF. But again, you'll remember from our second step that DE squared is equal to A, EF squared is equal to C, and DE times EF is equal to B, so we can just plug those back in and say that A plus C is prime to B, which is the last thing we set out to prove, which means we're done with the proposition, therefore, etc., Q, E, D. Now we're going to get into those steps where Euclid cites book 2 propositions to help him with a statement about numbers. Now, you'll remember when I explained where the language of square numbers comes from, where that came from is that you would represent a line, you would call that by a number 2, like this, And then whatever the area of the square on that straight line is therefore the square of the side. So if we have a straight line, we call that straight line 2. We number it, in other words, and we build a square on that line, then whatever the area of the square so generated is, will be the square of the number 2. And we can see that that holds. The area of this square with a side length of 2 is 4. So 2 squared is 4. How this helps us, this interplay between square number as just an arithmetic term, but also a geometric term, is why Euclid cites these book 2 propositions to help him out here. I'm going to use the citation of proposition 2.4, but this would just as well hold for proposition 2.3, but I only have so much space. What would be going on here, right, is say we have the continued proportion of 4, 6, and 9. We've used that plenty of times by now. 4 is to 6, just as 6 is to 9. Furthermore, these are also the least numbers in their ratio. So what we do with this information, we take the two numbers DE and EF, which for this proportion will be 2 and 3. And what Euclid does is he has two straight lines and he calls them 2 and 3. So what he's then going to do is he's going to put them in a straight line with one another, like this. So you'd have the 2 line and the 3 line in a straight line. And what he's going to do is he's going to build the setup for proposition 2.4. You might remember that. I mean, I know it was about a year ago at this point that I demonstrated that, but this is the sort of setup you would have. You would have the square on 2, you would have the square on 3 down here, and next to these squares, you would have two rectangles, which are equal to the product of the two straight lines. In this case, that would be 2 and 3. So the area of this, as I've said before, is 4. The area of this bottom square is 3 times 3, that's 9. So 9 is the square of 3. And then these two rectangles are going to be the product of 2 and 3, so they're both going to be 6, like this. And this is how Euclid is allowed to cite book 2 propositions to help him make a statement about numbers, because we can represent numbers as straight lines, or more accurately, we can have straight lines and we can give them a number, and then we can play around with those straight lines to get these geometric identities, and then plug the numbers that we gave them in to make a statement about numbers. So we know that this whole square on this straight line right here, this big one right here, is equal to the sum of this square, and two of these rectangles. If we give all of those straight lines a number, then what this is equivalent to saying is we would have a 2 and a 3 here. So what this whole diagram is that, 2 plus 3, that is 5 squared, because remember, we have also a whole square on this big straight line right here. So 5 squared would be equal to 2 squared plus 3 squared plus twice 2 times 3, which is 12. And that's easy enough to verify. 5 is 25, 2 squared is 4, 3 squared is 9, and 12 is 12. And if you add 4, 9, and 12, you get 25, which is 5 squared. So we see that this is a valid move for Euclid to do. He's going to make these straight lines, give them a number, and then translate statements about those straight lines into statements about the numbers he gave to them. This is not the last time you'll be seeing him do this sort of thing. It'll happen several times in the book after this, book 10, but this is the first time it comes up. So I wanted to spend a long time explaining this, because it is a weird step if you don't exactly know what's going on. I know I certainly didn't. That being said, I hope this was a good explanation of that. If there is still confusion, of course, the comment section is always open. And with that said, I'm going to end the video here and move on to proposition 9.16.